Yeah, no idea. All right, and we're back. So this is the second day of section 3.5. Now, I hope you guys got a kick out of my enjoyment of teaching this lesson. Implicit functions are just so cool. Like, they're just so fascinating. You're looking at me like I'm crazy. I know I am crazy. It's self-admitted. I know it. It's true. But implicit functions are ones that, just to kind of define it again, ones that use y within the equation. They're not only defined by x, but they're also defined by y, right? Normal functions that we have are defined just as y equals, but implicit functions have x and y both in the function themselves. And they make some like really cool designs. Like, man, it's like that, this Batman looking thing, yeah. Crazy. But the cool part about Desmos is Desmos actually graphs all of these things for you. And we looked at this one too. The x to the fourth plus y to the fourth equals 16. It's kind of like an oblong, like a rectangle, square with that rounded out corners there. Just remember that when you're doing double primes, y double prime, you can plug y prime back in. You should never have y double prime as an equation with y prime in it. Because you've already solved for y prime, so you need to take that y prime and put it back into y double prime. That was the very last example that we did on through the video. All right, so let's talk about. Maddie, scare me like that. I'm an old man. I could have a heart attack up here. I need to worry about this. Maddie, where are you going, Maddie? Wait, she already graded it. Let's see. Like, what? Yeah. We're gonna 2.96. Okay. Derivatives of inverse trigonometric functions. Now, if you guys notice, this is the last big box on the formula sheet. This is the last big box on the formula sheet. Derivatives of inverse trigonometric functions. So like the derivative of inverse sine of x, or the derivative of inverse cosine x, or the derivative of inverse tangent of x. And we have all 6 there. Inverse sine, inverse cosine, inverse tangent, inverse cosecant, inverse secant, inverse cotangent. Basically, why did we need to wait until right now? We needed to wait until right now because we needed the chain rule to define these things. Sine isn't necessarily inverse sine isn't necessarily an implicit function. Okay, it's not really an implicit function, but it's one that we would have needed the chain rule for. And I believe they just didn't want to add this into the chain rule section, one that like can get tacked onto the other end of the implicit section. But to actually formulate the derivative, you need to think about it as differentiating it with respect to like sine y equals x. Because isn't sine y equals x, y equals inverse sine of x, right? Sine y equals x is really like saying y is equal to inverse sine of x. So what we can do here is differentiate this, right? We can differentiate this and say, well, if I can find the derivative of that, that's going to be the derivative of inverse sine of x, y prime in the end, right? So now, the book gives all the proofs. Trust me, if you want a little light reading, the book gives all the proofs. But I'm just going to show you them here. For my purposes here, should I make you memorize all these? No. This is why I love teaching freshmen. Dang, that's a pencil. That one was right there. Yeah. That makes sense. So maybe and is this one of mine? I saw him walk up and get this pencil.
Who was it?
Little turd. No, I'm not naming. I'm not naming names, especially while on video. Anyway, these are the 6 derivative of inverse trigonometric functions. These are really weird. They have some, commonalities to it. Like, take a look here. Think about this. What was the derivative of sine? Cosine, right? And we've seen that working implicitly is kind of like working backward, right? Okay, the derivative of sine, inverse sine is this. Look at the derivative of cosine, the negative, right? The derivative of sine was the positive, the derivative of the cosine was the negative. So some similarities between the derivative of sine and cosine to the derivative of inverse sine and the derivative of inverse cosine. The derivative of sine was just positive cosine. The derivative of inverse sine is this positive thing. Right? The derivative of inverse cosine is this same negative thing. So it's that 1 over square root of 1 minus x squared. Now, the derivative of inverse tangent takes away the square root in the bottom. 1 over 1 plus x squared. The derivative of cosecant, inverse cosecant has that same look to it with the 1 over square root of x squared minus 1. But they tack on an x there. And remember, the cos were all negative. Right? Just like we had said with the derivatives of regular trigonometric functions, the derivative of inverse trigonometric functions follows some of the same rules. Okay? So the cos are all negative. The derivative, and they all got this 1 over square root of x squared minus 1 in it. The secant and the cosecant both attach an x to the outside of the radical. And the cotangent is the exact same thing as the tangent, but the co is just negative. Okay? So they all pretty much have this 1 over 1 and then an x squared in the bottom. Some of them are minus, some of them are plus. Look at the order here as opposed to the order here, right? The cosecant and the secant, the order is flipped. It's x squared minus 1. The sine and the cosine, it's 1 minus x squared. The cosecant and the secant both have the x attached to it. The cotangent and the tangent are extremely similar, but one of them has the negative. Okay. All right, so let's take a look at one of these problems here. Differentiate y is equal to 1 over inverse sine of x, and then we're going to differentiate fx equals x arctan x. Okay. All right. So let's do part A. Y is equal to 1 over inverse sine of x. Now, isn't 1 over a negative exponent? So, like, can't I rewrite this as inverse sine of x to the negative first power? Now, be careful. That negative 1 power on, like, that to the negative 1 is not saying to the negative first power. That's saying inverse, right? Be careful not to think, oh, that's going to cancel. It's not going to cancel. That's inverse sine, not sine to the negative first. I mean, we're all taking it to the negative first, but you get the idea. Now, to differentiate, what am I going to have to use? Have to use the chain rule. I have to use the chain rule. Here's why. I've got this to the negative 1 power acting on a separate function. So what I have to do here is take negative 1 times inverse sine of x to the negative second power, right? leave it as is on the inside for the first part of the chain rule. And then I multiply it by the derivative of inverse sine. Now, let me go back to my formula sheet. The derivative of inverse sine, 1 over square root of 1 minus x squared. Yep. So it's 1 over the square root of 1 minus x squared. Now, again, one of the only things that you need to do here to simplify it is to just get that negative exponent out of the way. So all said and done, this y prime is going to be equal to, looks like I got a negative sitting out front. The only thing left on top is a 1. This inverse sine of x times the square root of 1 minus x squared. And that's all I can do. Oh, raised to the positive second power. Sorry, forgot that. And that's all I can do to simplify it. What's another way to say arctan? What does arctan really mean? Isn't that just inverse tangent? Yeah, that's just inverse tangent. So f of x is equal to x arctan x, or sorry, arctan square root of x, is really like saying f of x is equal to x inverse tangent of the square root of x, right? Now, what's different between just saying inverse tangent and saying an arctan? Remember, arctan is that specifically defined domain, right? Just that specifically defined domain to make it a function. For our purposes here, when doing the derivative, it doesn't really change anything. All right, now, this is a tricky one. This is a tricky one because I see a couple different things going on. The first thing that I see is a product. Yeah, I see a product. I've got to use the product rule. Okay. The second thing that I see is that when I go to look at inverse tangent, isn't there a separate function within inverse tangent? So that's going to require me to do a chain rule in there. You've got to start thinking about what types of rules I have to do in the order in which I need to apply them. All right, so let's first start doing the product rule. Remember, the product rule on your formula sheets, it's f g prime plus g f prime. Okay, so my f in this case is x. So f prime of x is going to be x and then the derivative of g. Now, this is the chain rule part of that, right? So I've got to take the derivative of inverse tangent. Okay, the derivative of inverse tangent is 1 over 1 plus x squared. So it's times 1 over 1 plus. Now, what goes down here, though? Is it just x squared? Be careful. The rule for inverse tangent was just inverse tangent of x. I've got inverse tangent of the square root of x. So what I actually have to do is say 1 plus the square root of x squared. You see that? Because my input wasn't just x. My input was the square root of x. So within the derivative of inverse tangent rule, I've got to input what was in my parentheses. Okay, so that's the derivative of inverse tangent. I've peeled back the layer of inverse tangent, and now I need to find the derivative of the square root of x. Now, just remember the derivative, I'll put the work over here. Square root of x is x to the 1/2. So that would be 1/2 x to the negative 1/2. So 1 over 2 radical x, right? That's the derivative of the square root of x times 1 over 2 radical x. Please understand that this was all the derivative of g. When I look at my product rule and I say f g prime, that's all g prime because it required me to use the chain rule. Okay, plus the original g, inverse tangent of radical x, times the derivative of f. Oh, I didn't need to leave so much space. What's the derivative of f? Just 1. Okay, so let's reduce it down a little bit. Yeah. So f prime of x is equal to, looks like I've got I can put the x on the top. 1 plus, isn't that just x? Square root of x squared plus 2 radical x plus inverse tangent of radical x. Oh, hold on. Whoa, hold on. Hold, please. Whoa, I made a boo-boo just in this last step. That's not plus down below. That is times, right? That is times there. So that x still stays on top. But what I have to do is look at this. That is not plus 2 radical x. That is 1 plus x times 2 radical x, right? So on the bottom, that just to finish that off, that'd be x, 2 radical x, plus x times 2 radical x. That's just 2x radical x. Plus inverse tangent of radical x. Honestly, this would have been an acceptable answer. Down here would have been, I mean, we just distributed the 2 radical x. Either one of those would have been fine. Yeah. Questions on that? Okay, I'm going to stop the video and then I'll answer any questions that we need over anything. You can ask me anything.